In the meantime, do you have any questions? Have you thought about something during the break, or you want to forget everything already? No. Enrico, come on. Okay. Everything is clear. Okay. So again, when we start, we want to kind of have a recap of what we did or what we have just done, right? So in this second part of the talk, we talk about Bayesian networks, right? We again started from an example, which we have few variables. And in this example, we build the graph, the dark. And then we realize, okay, we usually don't have the conditional probability tables, right? We want to start from the data. And then we want to learn from the data a possible structure of our DAG, okay? Which is, let's say, in other words, a possible model, right? The model implies some conditional independence assumption. We use these conditional independence assumptions to find queries, right? We recover a graph. We were very happy about the graph. And we talk about also the separation. What was the, let's say, characteristic of the separation? Was that? Yes. Okay, let me tell in other words. Enrico said, okay, it helps us to understand which conditional independence are true in the graph. So if we say two nodes are separated, we are saying that they are conditionally independent. So if we want to read from a DAG the conditional independencies, then we need to use the deseparation, not just the separation, which is a different concept. Okay, so the question now is, in the second part, we talk about Markov random fields or undirected graphical models. And the thing is that here we have undirected graphs. So the question is, why do we need undirected graphical models? Why cannot we stop with directed ones? So I told you a motivation, and the motivation was about, let's say, C2 nodes to random variables are correlated. There is no asymmetric, let's say, behavior between two variables, two nodes, right? But there is more symmetric behavior, right? The other ones is that sometimes some conditional independent structure cannot be put in the DAG. So you have some particular structure which is not possible to put in a DAG. Okay, we will show this one. So, like, it's very specific stuff. So sometimes you want some conditional independence that is like that, but you cannot represent with a DAG the conditional independent structure that you have for your problem. Okay, that's the main motivation that has to guide you. So this is the example that I will give you. So we have 4 students now, which are our nodes or random variables. they can, so there is a professor that talk, and sometimes students understand the topic, sometimes they don't, because the professor is not clear, let's say, okay? So we have these students, they can or not understanding something, let's say a subject or a definition, whatever you want. And it's because the professor is not clear, okay? So there is a misconception from the professor to the students. And for some reason, these students here, not all the students communicate with each other. This means that, okay, Alice communicates with Charles, okay? Charles talks with Debbie, but Bob, which is the other student, and Debbie had a relationship that ended badly. So they cannot stand each other. So they don't talk to each other, okay? So there cannot be a connection between Bob and Debbie, as well as there cannot be a connection between Alice and Charles, because they don't like each other, so they don't talk. So if I have Alice and Bob, okay, and they have information about whether they understand correctly a definition or not, they can help each other, okay? Bob and Charles, they can help each other. Charles and Debbie, they can help each other. Debbie and Alice, they can help each other. But for example, Alice and Charles cannot stand, so they cannot help, okay? So we have this. How do I translate what I said in words in conditional independence assumptions? Help me. So I can translate this in this way. So we have that A is conditional independent on C given B and D. Okay? And then we have B is conditional independent of D given A and C. Now, the challenge is try to represent these conditional independencies with a DAG. Try it. So I gave you the independence, I gave you the problem. Now try to put in a DAG, respecting these assumptions. You have to build a DAG. You were thinking about it. Yes, the answer is not possible, but we are trying. Have you tried something? Okay. Let's give some couple of minutes because I see some notes, but I don't see arrows. So why is it's not possible? What did you try, Laura?
That the conditional independencies are is independent on its non-descendants given its parent. And basically we have that B should be a parent of A, and then that A is a parent of B, which well, is
Okay, that's okay. You put it like there is a direction, but I don't have a direction in the assumptions. Let's say that A communicates with B, but not the counter. So you can kind of put an arrow. Let's say AB, BC, okay? And then you have AD. And then you take this one as a graph. Something like this. The question is this DAG giving you the conditional independencies that we want? That's the question. So the problem is, look at this. For example, D and B, we said that they should be conditionally independent given A and C. Or A and C, I don't remember. But let's say D and B should be conditionally independent given A and C. Now, do you remember the definition of D separation? Yes. Yeah. So you have a V structure, you see it here. You have the collider, which is in the set of separators. So they are not D-separated. And what does it mean? That D and B are conditional dependent. Okay, but this is not our assumption. If you look at this one, it looks like we get what we want in our mind because A talks to B, let's say B talks to C, C talks to D, and D talks to A. But when we look at the conditional independence, then we don't get the structure we want. Okay? And put in another way, you can put like this. This is just changing some link. But here, if you look at D and B, again, you have a problem with conditional dependence. Okay? So these structures, whatever structure of DAG you think about, it's impossible to codify the conditional independence we want in a DAG. So we need to change something, right? And what we change is the set of conditional independence in this way here. So we introduce an undirected graph which has different Markov properties, the global, local, and named and pair Markov properties that comes from a different factorization of the joint probability distribution. We'll see that, okay? So this means that, do you remember the factorization of the DAG? Okay, this is not anymore our factorization. It's going to be something different, okay? That is what, and we want some factorization that is different to catch the conditional independence here we want, okay? Yes? Okay, so this is just a summary of what we have just said. And the other difference between the Bayesian networks and the undirected graphical models is about the conditional tables, conditional probability tables. Why? Because when we use undirected graphical models, we don't have anymore the parents, so we cannot condition on the parents, and we don't have any more conditional probability tables, but we rely on something called factors. Okay? We will indicate the factors as this phi. So this means phi A and B. This means that the nodes variables A and B are neighborhood. We know what neighborhood means, right? First part of the course. And it means they kind of have some higher number now. Before was probability, now it's a number. It's not a probability. To be, let's say, 1, 1 here, then 1, 0. Because if one understands, the other understands as well. Okay, the misconception problem. These factors are not probabilities. Okay, so in order to make the factors probabilities, we need to divide these factors by a normalization constant. We will call this Z. We will see in a moment. Okay, I will give you the scan. Okay, now, do you remember the factorization of the DAG? It was a probability, a product of conditional probabilities, and the conditional probabilities was one node given the parents, right? Here, the factorization of the joint probability is given by the product of factors. These phi are the factors we said, right? In these factors, I have to put this C, which are the maximum click of the undirected graph. Okay, so if we go back to our problem, oops. Okay, here, what are the clicks, maximum clicks of this undirected graph? All the couples, so it's AB, BC, CD, AD, right? So the factors that we have in the factorization are going to be phi, right? Of the first click, let's say C1, will depend on A and B. Of the second click will depend on B and C. The third one, C and D, and the fourth of D and A. So you have 4 factors that will depend on 2 variables. A and B, and C, C and D, and A and D. Okay, that one is the factorization. Now, the product of these factors is not a probability anymore. Okay, like before, we said, okay, we have conditional probabilities, we multiply, that was the joint, right? But here, the product of this factor is not a probability anymore. So we need to divide okay. Here, okay. So these are all the couples, right? So you see A and B, they can take value A0, B0, A0, B1, A1, B0, and so on. All the factors, you see this is 35, 1, 10, and so on. And you can realize these are not probabilities, right? Correct? Because it's not between 0 and 1, they don't sum. Okay, now I have to combine these factors to get the joint. And this is what I obtain. So these numbers here. So for each combination of my 4 variables, I obtain one of these. And then if I divide this by Z, which is the constant of normalization, which is the sum of all of them, you obtain the joint probability. Okay? So the formula is here. So you have P1, we say depends on A and B. phi2, which depends on B and C, and so on. Okay. And then you have this Z, which is a sum. Well, this is you see one sum, but it's four sums, right? It's because it's over A, B, and C and D, okay, of this product here. And this means I'm normalizing the product of the factors. Yes?
There are advantages because the initial number of parameters.
Yes, yes. Because each one of these will depend on two variables. The initial one will depend on four. So you have a reduction of the number of parameters. Yes. This one is like similar to the one before. Doesn't change. So you have a reduction on the number of parameters. Yes.
Are the factors related to the weights, like a weight associated with each?
Yes, the weight of the factors, so the number that you assign to the factor, is related to the fact that, for example, Alice and Bob, right? They give the answer 1, 1. Okay, so if they are more in agreement, so you assign an higher factor to this combination. It's similarity. Then you have A and B, like A0 and B1, which means one has misconception, the other one has not misconception, so you have a low number of this combination of factors. If
the weight.
Probability, yes, exactly. And then you can talk about probability. Correct. Yes.
So we're considering as an example a case in which leads actually coincide with edges.
So if you mean how we construct this one?
No, I mean in this case leads are made of a couple of nodes, so
yeah.
There's actually a one-to-one relation with edges, right? In this case.
Yeah, okay.
So the question is, if there were, for example, like a made of three, would we assign a factor to the grapple?
Yes. Okay. I now understand the question. So, in other words, you are telling, like, okay, where is the graph? Here, I put a link between D and B.
Yes.
Let's say they kind of break up, but then no, let's make peace and stuff like that. So they kind of are connected right now, right?
Mm-hmm.
So you have now how many clicks? Maximum clicks? 2, because you have here. Can imagine a link, and you have A, D, B, right, and D, B, C, right? So when you create the factor should contain one is phi of A, B, D. Okay, so it's 3. Okay, and then you need to have all these combinations, and the other one is D, B, C. Okay, so in your product, it's going to be here, phi C1, which contains A, B, D, and the phi C2, which will contain D, B, yeah, whatever. Yes.
Is there any loss of information when we aggregate together and we consider clicks instead of the,
So when you use conditional independence, you are simplifying the problem. So in other words, when you simplify the problems, you go away from your table of probabilities, right? So you have a true table of probabilities. It's like linear numbers. If you have 3 variables there, and you kind of put an interaction of 3-way, you recover exactly your table, right? Because you recover probabilities exactly. You don't model anything because you don't lose any information. Whenever you assume one independence, you are losing information. But the question is, I mean, I'm losing this information, but this information is not too much for my data. I mean, if I change just one subject in my dataset, the probability table will change, right? And so the complete graph is not going to be useful for my dataset with just one different subject. Yeah, so it's like when you parameterize a problem with n parameters and you have n subjects. Okay, I recover exactly the points, but I'm not losing any information, but I'm giving too much information. So there is no flexibility in the model, you know? So you kind of imagine this axis, right? And you want a non-parametric regression. You just pass by all the points. So you have as many parameters as your number of points. You don't lose any information, but you are not summarizing anything. Whenever there is a new point, even if it is close, it's far from your model. So you need some flexibility. How much flexibility you can lose in the previous example were determined by the BAC score, right? Because you assign a score to a network, you say this other network doesn't give me more information that I had before by kind of putting somehow a weight between the likelihood and the number of links you have. Okay, so you do this balance. And then you say, no, I don't need this other information. I don't need this other conditional dependence. Here is the same. Yes, you lose information, but you have to be willing to do that, okay? Okay, good. So, other questions? Like questions? No. Okay. We have already said something about log linear models, right? Do you know log linear model, by the way? Have you used them for contingency tables? Maybe some small contingency tables? Yes? Anyway, I will give you some hint again. So here I change a little bit the data. So now we have a data set, data frame in this case, which is a contingency table of dimension 2 up to 6, because you have 6 variables. This is a study, a prospective study on coronary heart disease. It's an old study. And so you have these variables: smoking, strenuous mental work, strenuous physical work, systolic blood pressure, ratio of lipoproteins, and if you have some history of coronary heart disease in your family. Okay, so you have all these variables, and then you want to kind of model this. Again, what do? You can do a Bayesian network now, yes, or you can use log linear model, right? Okay, so some notation. So the random variables are going to be represented by this y1, y2, yd. More in compact form is like this. Then the cardinality of each random variable is going to be the number of categories that you have for each random variable. And then you have a generic observation of your contingency table represented as this I1 ID. I will show you an example in R, just to be clear. And then you can express your row case list as an aggregate case list. What do I mean? Okay, so let's go back to the example. You have these 2,000 workers, right? You interview each of them. Here, and you ask, do you smoke? Yes or no? Do you have strenuous mental work? Yes or no? Do you have strenuous physical work? Yes or no? So you have, at the end, you have a table, data frame, right? In the first row, it's going to be the first subject, right? Which answer all these questions. So it's yes, yes, no, no, yes, right? The second subject is going to be the same combination, let's say, of the first one. The third one is going to be a bit different. So at the end, you will have different combinations, but some of the subjects will have the same combination, right? So you can aggregate all of them. You can take all the possible combinations or your 6 variables. Let's make 3 variables, 1, 1, 0, okay? You can have 0, 0, 0, 0, 0, 1, 0, 1, 0, okay? So 8 lines which aggregate your data and put at the end a frequency. So this combination, 0, 0, 0, has been present 50 times, okay? So 50 subjects as this combination in my data set. Then 100 subjects as the second combination, and so on. At the end, the sum of your frequencies should give you what? The number of subjects that you interviewed, right? Okay, okay, let me know the example, but okay. So which kind of sampling scheme can we have? We can have 2. One is that also counts and the total number of observations are random. And one is that the total number of observations is fixed. This sampling scheme should help you to understand which distribution you should put for your data, okay? Anyway, so it's in the first example, we have the Poisson distribution, and the second one is the multinomial distribution. I hope you are familiar of the Poisson and the multinomial. Anyway, you know that you can go from the Poisson to the multinomial and vice versa by some assumption. Okay. So now we have this pi I. What pi I is representing is the probability of the joint probability of a combination, right? So it's if you think about our data, you have I don't know, yes, 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 okay, and this is one of these I. And what is the probability of having answered all the questions yes? So you do a stressful work, you have a family history of coronary artery disease, and so on. So you have this combination. And this pi I will represent this, okay? This probability comes from the multinomial. Then if you have three variables, which are binary, you can have how many I can you have? So you have 8 I's, 8, okay? So you have 0, 0, 0, and you have a probability of this. 0, 0, 1, and you have a probability of this combination, and so on. And you model this probability, okay, with log linear models, which means you have these factors, U, which are related to the variables A, B, and C. Okay? So here you have the main effects, A, B, and C. Here you have an interaction term. Okay? And here you have an interaction term where you have all the three variables together. As we said before, if we have three variables, do you remember the name? Francesca. We were saying, okay, if we model like this, the joint probability of this, we will get exactly the table, the contingency table we started, right? So we do in the what we do in the log linear model, we make some assumption. For example, we remove this term, so the interaction of the three variables, and then we can remove this. This is called main effect model, right? You have worked with that, okay? But I don't know. Have you ever think you are removing something? What are you removing? Are conditional dependencies. So the main effect actually is going to be like a graph with no edges. Okay, so when you use that one, it's like A, B, and C, they are not connected. So there is no link between anything. That's the model here we are using. Okay? Yes?
But if you consider only the third the direction down the three roads, how does it impact in the graph?
Yes, exactly. This is what we are where we are going. So no, Virginia. In other words, you asked how the log linear model is related to the graphical model. We haven't said that, right? We are going to have a look at it in a moment, okay? Just a few slides, Virginia. Yeah, okay, but it's a good question. First, look at this model here, okay? Where you remove the term with the three variables, A, B, and C, and then you remove another term, which is the combination between B and C. You see there is a couple here, A and B, there are a couple A and C, and there is no term B and C. Yes? So you have here this A and B and A and C are called the generators of the model, of the log linear model. Okay? The generator. And well, you can, what we are doing here is split the joint probability in two parts. One part will depend on A and B. One part will depend on A and C. But what does it mean, this one? This means that we factorize the joint probability in two parts, in two factors. Phi, this is phi A and B, times phi A and C. So it's like you have two clicks now, A and B, A and C, right? And you imagine this graph joining A and B, A and C. Yes? Okay. And now we have conditional independence of what? In this case, it's written here, B is conditionally independent on C given A. Okay? So you have B, A, C, A, but you don't have anything about B, C. Yes? Okay. Now, I forgot to tell you, we are talking about hierarchical log linear graphical models. Okay, so there is like if you put a term of, let's say, two interactions, the previous terms needs to be there. Okay, this means that if I put A, B, C, then all the terms before needs to be there. That's hierarchical. Okay, now look at this one. This hierarchical linear model is something like this. I hope you can read it, but it's the main effect model. So you have S, F, D. So you have this conditional independence because you can factorize the joint probability. This log shouldn't be there. No, it should be there. So yes, in 3 parts. This doesn't depend on anything else. So you have this one. And the graph corresponding to this hierarchical model is this one. So you don't have any link. There is no connection. Okay? Now you have here, you put the main effects, and then you put SF, an interaction term, and SD, the other one. So the generator of this graph are SF and SD, because they are here. And now you have this conditional independence, which means you have this undirected graph. So the question is now, can we conclude that all the hierarchical log linear models are graphical? That's the main issue. And the answer is here. The answer is no. Look at the graph above. So you have this graph here and this graph here. Yes? These are the same, right? But look the hierarchical model that I can take from this one and from this one. Are these two log linear models the same? No. Why? Because there is a term here, right? Which let interact the 3 variables. But the graphs are the same. So I cannot represent both. So there is something missing, right? There is something missing in our definition, let's say. Because to be graphical, so it's like graphical log linear model, the generator of the model must correspond to the click of the graph, the maximum click. And now you can say that it's graphical. So hierarchical log linear model are graphical if the generator corresponds to the maximum click of the graph. And here you can see this is a simple example. What is the click of this one? What is the click? I know you are tired, yes, but what is the maximum click of this one? Yeah? The whole graph. So it's state, fever, and this, right? Now, what I said is the generator of the hierarchical model. What is the generator? It's given by F, S, and D, right? What is the click? F, S, and D. So now they correspond, right? So this model here is hierarchical and is graphical. Now let's go here. What is the click of this one? The maximum is the same, right? What are the generator of the hierarchical model, they are SF, SD, and FD. But this doesn't correspond to the clique of the graph. So this model is hierarchical log linear model, but it's not graphical. What does it mean concretely? That you cannot use what the theory of the graph, so Markov properties, gives to you if the model is not graphical. Okay. Yes, Virginia. I think this more or less answer your question.
Yes.
Okay, so this is the connection. Okay, I think I have, yes, here the formal definition, so you can read it, but it's what we discussed about. Che ora è l'altro break è mezzo, giusto? 3:30 l'altro, quindi c'è 30. Ok, we have time. Ok, good. So any question? Yes. Yeah.
In statistical theory,
Uh-huh.
when we ask, for example, in slide 24, it doesn't correlate figures. We are like when we have an hypothesis, which is u FD is equal to 0, the constraint model,
Yes.
it like considers. You say like
It's like a hypothesis test where you put that one equals to 0. Yes.
Even for the others, coefficients.
Mhm.
Because they are 0. So it's strange to say that if F and D are conditionally independent given S.
This one here is strange for you. Okay, where did this come from? That's the question, right? It's like
since we have new FS, we have new XP.
Yeah.
In some sense, we have the edge.
Yes, but the question you have to ask yourself is, can I factorize it? So can I split this without having a factors that contains all of them? That's the question. So if I can write this one, this bit here, okay, with two factors, let's say P1 and P2, one that contains just S and F, and one that contains just S and D, then I'm fine, because I respect the definition of factorization. And that one tells me something about the conditional independence, okay? I don't know whether I answer your question, but that's more or less what I did here. So it's this one is my joint probability. The one that we saw before was with A, B, C, D, stuff like that inside, and then I split it in two parts. One that depends on just A, B, C, and one that depends on D, whatever you want. But these two parts can be splitted without putting something that is here inside here, and vice versa. And then I can factorize this. Okay, then these are factors, it's true. These are factors. So the product of this is not product of two conditional probabilities like before. But anyway, I can normalize this stuff. That's the point, because this is exponential something. Expo. Huh? That's the point. The whole point is there. So if I can kind of factorize according to the definition of factorization of the graphical model, undirected one in this case, I'm fine. Because I know that if I factorize in that way, I prove that they are conditionally independent. Conditional on the rest. So these two. Okay. Other questions? This was an interesting one. Yep. No? Okay. Okay, so you know that when you have contingency tables, you transform the raw data in aggregate data. You have this column of frequencies. You can model this as Poisson, independently distributed. So you have a number, right? It's a frequency there, and you can model it as a GLM, right? So the problem is that when you try to apply the GLM to our data, with few variables, let's say 5, 6, 7, the iterative weighted least square algorithm doesn't give you good results. Actually, it doesn't invert the matrix that you need to invert to find the solutions. And so often you get computational troubles, right? So you cannot use the, let's say, theory of generalized linear models, and you need specific algorithms to overcome this problem. Moreover, if you think about the GLM, the scope of the GLM is to find, let's say, to estimate the parameters of the model, the log linear model or the Poisson model. But in this case, our aim, our main aim, is not about the parameters, it's more about learning the structure of the graph, right? Which is a bit different. Okay, so we want to focus on that one. And for, let's say, many years, people worked with decomposable graphical models, right? Because they were, let's say, manageable in the sense that you can obtain closed form, okay, of closed form for the maximum likelihood estimate, and then it's I mean you don't need iterative algorithms to estimate the parameters. Now, well, we have other algorithms, for example. Okay, to have it here, yes. Sorry. Okay, this one, the iterative proportional scaling, that helps you to answer your question even for not decomposable graphical models. Now, what is a decomposable graphical model? You did a task and didn't tell you, so it means you are very tired. So what does it mean to have a decomposable graphical model? A decomposable graphical model is a graphical model, undirected one, which is not chordal in the sense that, let's say it's written here, so, which is chordal, sorry, not chordal. So you have, in the undirected graphical models, you have graphs that are undirected, right? And these undirected graphs can create loops, let's say. Okay, so let's say you have A, B, C, D. To have it here, something like that. Okay, so you have this one, A, B, C, D. Okay, and you remove this link here between B and D. Okay, so you have here, let's say, a loop from A to 8, which goes in 4 steps. Okay, so this is not chordal. So at most you can do 3 steps there. Okay, so if you have 1, 2, 3, 4, okay, in order to make it chordal, you need to make a chord, okay, a link between these two. And in this case, you will remove the non-chordal graph. Okay, so in this case, you can prove by using this property, which I think I'm going to skip because otherwise you won't arrive to the other half an hour. Anyway, it's you can have a look. It's called reordering the graph. It's like ordering the clips and then finding the solution of your maximum likelihood estimate for the multinomial sampling scheme. Okay, so this M is related to pi. Pi is our joint probability, right? So this M is just given by the number of subjects that you interviewed, pi multiplied by the probability. Yes? So if you want to obtain an estimate of this one, and you have a full graph, which means a full model, then you obtain just n pi, so the number of subjects divided by n. That's it. That's the maximum likelihood for multinomial, okay? If you have a graph that reduces the complexity, so you remove some links, then you need to use this formula, which is in Markov form. So I obtain the estimate of, let's say, pi, because if you divide m hat by n, you obtain pi hat, by dividing this by, well, these are subtables that you obtain from your main table, okay, through the reordering. Otherwise, well, you use the iterative proportional scaling. Okay. So the package that implements this stuff is called Grain, and we are going to use it. Well, inside it relies on the deviants. I guess you all know, are all familiar with deviants, more or less. And mainly the model selection stuff is doing again by scores, and the most common scores are again the archaic information criteria and the Bayesian information criteria. Okay, these are the two alternatives. Okay, almost done. Okay, the theoretical part, let's say I skipped somehow some technical details. I'm sorry for that. If you are like, okay, no, give me, I will give you, but I see your faces, so it's better not talk too much about the theoretical stuff. It's all there, okay? If you want to just go into the details of every slide, it will take a little bit more effort, of course, but you have everything in place. The thing that I want to stress here, it was that we have a different graphical model. So we have the directed ones, the Bayesian networks, and the undirected ones, right? For the directed ones, we took an approach. I didn't show you like the log linear model or the assumption about the joint probability distributions. I'll show you from the conditional probability tables how to obtain the joint probability tables, and from the data how to obtain the Bayesian network, estimate it, answer to queries. Yes? Okay. Then everything inside is okay on your own, let's say, okay, to go deeper into this. And there are algorithms and stuff like that. In this case, we went a bit more on the models, right? We introduced the log linear models, the hierarchical log linear models, and we kind of relate the hierarchical log linear models with the undirected graphical models. But why did we take this step further? Because we need some conditional independence that wasn't present in the previous framework, right? Because we did have an example at the beginning where we want some conditional independence and we couldn't make it with DAG. Yes or no? Then we kind of arrive to the end, and then we have this the analysis of well, the BT study on this tribu, tribe in English, tribe of Pima Indian woman, and this data set. Well, I will show you in R that contains these variables. So you have how many, the number of times the woman was pregnant, the glucose, the level of glucose at 2 hours made by glucose tolerance test, the pressure, so diastolic pressure, the thickness of the triceps, the insulin, the BMI, the diabetes pedigree. So this is actually a number, the age and the test. In this case, we have mixed actually variables. And what I did on R was just to go kind of on Wikipedia, try to understand which values were normal or not in each of these variables, categorize them. So I put every variable in a discrete way. So we were talking about that. And then I try to model it as analytic graphical model, okay? I will do this on R. If you have questions on the theoretical, let's say theoretical part, it's time to make questions. You can think. In the meanwhile, I change the questions. Yes, tell me.
Well, wondered if all the hierarchical optional also graphical. I didn't get how should we that really graphical.
Yes. Okay. So
I got that both cannot be graphical because otherwise we should use the same graphical model. But I don't get why the second one is graphical.
Okay. So the main thing is to understand the difference between the generator of the model and the clicks of the graph. So these are two things that are separated, okay? So the generator of the model, you read the generator in the formula, which is log of pi I, and then you have this mu, right? A, B, C, then A, B, B, C, and so on. So the combination of these are the generator of your hierarchical log linear model, which is one stuff, okay? Then you need to look at the graph. And you say, okay, the clicks of my graph are this, this, and this. Now these are two separate stuff, right? But now you have to see whether these clicks, maximum clicks, correspond exactly to your generator. Okay? So if you have this matching, then your hierarchical log linear model is also graphical. And then you can use the Markov properties of the underrated graphical model. Did I make it clear or not?
I think that it is a choice that between the two linear models, so we describe the second one to the graphical model, or it's actually possible to describe the first one to the graphical model? Because looking at
no, it's okay. If you look at this, it's like the hierarchical log linear models are contains the graphical log linear models. So it means that in the hierarchical log linear models, you have more choices, okay? But you have less properties. So some of them are going to be also graphical, but not all. It's not a choice. It's something that you have to show, okay? So if you make the constraint that your generator are the clicks, then it's fine. But it's a restricted class. So it's like you have log linear model, right? Which is the bigger box. Then you have inside the hierarchical log linear models, and then you have inside the graphical models, log linear models. Actually, inside you have the composable inside again. Okay, so you have these boxes. It's like a matryoshka, right? The smaller is in the decomposable log linear graphical models. Yeah, more or less. Okay.
Let's assume that I have a hierarchical
Mhm.
okay. Can I check whether that login model
Yeah.
is also a graphical?
Yes, yes. Actually, there is a function in R that tells the
So,
is dot graphical is called. So you call the GLM, you have that one, and you can understand whether it is graphical or not. Yes, you can check it.
yeah, okay, so
But you start from GLM in that case.
yeah, okay, well, I don't need to know in advance graph, and to compare it.
No.
That is just something that I
You
assume
can do-
there is a graph, but,
It's like you build the graph from your hierarchical log linear model, but if it is graphical. It's the other way around, okay? So you estimate a hierarchical log linear model and you use it to say something about the graph. Okay, but this is not the algorithm that I suggest to use. Because whenever you have 5, 6 variables, then doesn't come anymore. Yeah. Yeah. Okay. So let's go back to our problem with so this is more or less what you have. So you have see the number of times the woman was pregnant, the glucose, diastolic, tricep, and so on. As you can see here is almost all the variables are actually continuous, okay, except test, which is not. And I kind of choose to categorize all these variables, okay? It's strong choice, but anyway. So you can do some preliminary analysis, see whether there is some problem. For example, the glucose is 0, so it's a bit strange. The diastolic is 0, so it's strange. You can do some nice plot, let's say, just to see the distribution of the pregnancy. So look at this. This is fine because when I looked at this bar plot, I said, "Oh wow, that's amazing, right?" They kind of have some issue with pregnancy with respect to our society, right? So there's someone who has 17 child, but it's a lot. And the distribution is, yeah, it goes down, but really low. Okay, so they are really kind of old people. Then, well, you have the distribution of glucose and so on. Okay, we skip the categorization, but you can find the code in the folder that we have shared with you. At the end, you have a lot of things. Okay. I have used also a function, if it happens that in the data set you have some not variable data, it happens in reality, right? You can impute them. I used here this forest, but you can use whatever you want, okay? I did prefer this one because it's related with, let's say, the tree structure, so it's related to the graphical models in a way, and it does the imputation quite well. So the data are missing at random, and there are other assumptions, okay? But you can use this function if you want, otherwise you can use whatever function. This is just to tell you that when I give you the data, don't start applying the graphical model. First of all, look at the data, see what is there, right? Do some nice plots, have a feeling of the data, summarize them, and then try to do the graph, okay? And this part is this one. Then you have the graphical model, which is here, okay? So the function is d mod. The d is for discrete log linear graphical models. You have also C mode, which is for continuous. I think there is also M mode, which is for mixed. Sure. And then you find this one. Okay, so you have tilde, dot, this, and dot again, which specify where you want to start. So, do I want to start with an empty graph, or I want to start to a complete graph, or I want to start with some specific graph? This is what I can give here, this dmod function. In this case, I'm starting with the saturated one. When it is possible, I start with the saturated one. Why? Because if I go back from the saturated one to the simplest I can obtain, I can be sure that what I obtain is a graph that well represents my table. Okay? If I start with an empty and I go up, doesn't mean that that one is going to be a good model for my data. If I start from the saturated one, okay, I decrease as long as the score, okay, tell me, okay, you can increase, you can remove this conditional independence, you can remove this one, you can remove this one. But then I stop because the kind of the distance between my data and the estimated one is going to be too large, okay? If I start from, let's say, the empty model, I go a little bit, but it doesn't mean that this is a good model for my data, okay? So whatever you can, you start from this one, and you do stepwise with, well, you can choose the direction. Of course, if you start from the saturated model, here you want to go back, right? It's backward model selection. So you start removing an edge, removing another edge, and so on. Well, this one type is decomposable or not, and this depends a little bit on how much you want to be sure about your final graph. Let's say that if you have a lot of data and you have few variables, okay, you can use not decomposable models. You are quite okay. But if you get a lot of variables, even if you have a lot of data, then you will be in trouble because you have sparse tables, okay? And for non-decomposable models, you kind of cannot be sure about some properties, let's say. Okay, the composable models work more on a subset of the graph. So it's like you decompose the model and you have kind of 100 variables, but you are working on 5, 6, 7. Actually, there's something that tells you you have to consider the maximum, the clique that is larger, that contains more nodes, and that one is kind of the dimension of your model. It's something, roughly speaking, is something like that, okay? So when you have, my suggestion is, okay, if I have enough data, a few variables, then use non-decomposable because it's fine, and I have more choices, right, for the graphs. Otherwise, be a bit more careful. Yeah? So you do this model selection. Of course, the non-decomposable is going to take more time because it's an iterative algorithm. You get something like this. Okay, these are the generator of our model and also the cliques, right? Because we said that they correspond. So if you want, you can put this in a GLM, this formula here, or you can build a graph. How do I build a graph? Like this one, tries insulin and test, is my first click, let's say. They are together, related, right? So here you have your second click, which is glucose, insulin, and test. Here you have your third click, tricep, BMI, test, and test, and so on. Okay, you can go on. Okay, I want to represent this one because like this, it's a bit difficult to see the graph. And if you want some information about the code, just ask. The code is there, I mean, that's fine. I'm trying to give you some hint about model. Okay, this comes from the model selection on the composable graph. Okay, so I don't expect a chord there. So I expect that here at most I have 1, 2, 3, you see, but not 1, 2, 3, 4. So there should be a link here because that one is not in the class of model I'm estimating. Okay. Can you tell me something about this model? Now you know about the graph, you know about conditional independence. You need to interpret this model. So you need to go to the doctor that asks you, okay, look, I have this this problem with this woman. I want to understand something. Please run a graphical model and then tell me about it. What are you going to tell me about it? This is, I think, simple to interpret, right? This part. Age, diastolic, and pregnant. So I guess if I'm older, right, my diastolic pressure is going to be higher, I guess, than if I'm younger. If I'm older, I have probability higher to have more child, right? So these connections are kind of expected, right? So if you tell me something about age, these two are conditionally independent, otherwise they will become independent. But not because there is a direct connection between diastolic and pregnant, but because there is age that influences both. So in other words, if you look at it like marginally, you will conclude there is some connection between diastolic and pregnancy. So it's like, okay, it's a risk factor for diastolic pressure, but it's not. It's the age that is the risk factor. Yes? It's like Simpson paradox. And then we have this test. The test is about being being diabetic or not. Grazie, te lo faccio più. Diabetic or not. And the test is related with history of diabetes. It was history. BMI, well, yes, of course. Triceps, so you have here, if you have more fat, then it's a risk factor, let's say. Insulin and glucose. So all of them are related to tests. Yeah. So this is interpretable, yes. If I give you the table, then it's a problem. But if I give you this one, then you can interpret it, right? Okay. So, well, you can use again TK plot to put your nodes or whatever you want, stuff like that. And again, yes, of course, yes, sure, sorry. Huh?
I know that PIMA dataset contains a relatively high number of anomalies and
Number of?
anomalous
Yeah,
Did you remove that?
yeah, yes.
Okay.
So for example, there were 0 in insulin, I guess, or stuff like that, which were strange. I put NA, so and then I imputed in a nice way. Yes, I worked before, so if you look at the code, there is.
Okay, and if you had included those instances now,
Yeah.
would be.
Yeah, that's a good question. So you can try to do it with this issue or without. And this tells you something about how much the graph is stable, right? So if I change something in my subjects, because I have outliers, this is what they are, right? How much the outliers influence my final graph, which is what I really need. Well, this depends, of course. I can't tell you because I didn't run the other test, but it can be that the graph is not much influenced by outliers. I mean, it's not like in regression. You have just a point, and then you have kind of the slope that goes another way around. No, it's not such a stable. But it depends on the cases, right? So, my suggestion is always to test how much is stable, even impute some lines, you know, that are not really in line with what you observed, in order to see whether some link is there or not. Yes, it's a good question. Yeah. There is even the function perturb that we saw before. It's like it's giving some perturbation to your data to see whether it is stable. Yes, there was a restart. You remember perturb, right? The restart start from other initial graphs, just not to go in the local. Okay. And the perturb does something like we are talking about. Okay. So there is here again the function grain that we saw before. You remember when we compiled and propagate the graph. This time I want to show this one. This here, the smooth function. When you have 0, right? 0 probabilities for some combination, then it's going to be a problem because you multiply 0 by everything, it's going to be 0 always, right? To avoid this problem, when you have sparse tables, Okay, I suggest to put this move very small, let's say 0.01. Well, you can read it like it corresponds to a prior distribution at Dirichlet, an informative prior distribution of on the probabilities. If you are Bayesian, then you can put like this. Or if you want, it's just a way to overcome a problem with zeros. That's your choice, okay? Then you have this compile, and then you have the queries. This last bit is again equal to the previous one. So you can ask as many queries as you want. And the way you do it is with the function query. Okay. Something like this. And this is conditional query, which asks, okay, give me the conditional probability of test, giving BMI, age, and insulin. So the fact that we are not using directed acyclic graph doesn't mean that we cannot answer to conditional probability questions, right? That's the point of all of this. So you want to answer these questions, and the best way is like this. Last thing, and then I will shut up. It's okay. So you can use this. I don't know whether you are familiar with these packages, ecosograms, something like this. It's a nice way to represent the conditional independencies. Okay, how do you read this one? So the, let's say, y variable, the one that you condition, is on the left. So it's the test here. Okay, the test can be 0 or 1. And we condition this test to 3 variables: BMI, age, and insulin, right? And here, well, I cannot read anything, but there are all the categories of BMI ordered. Here, so you have all the categories of age, and here you have all the categories of insulin. So within insulin, you have the first block, which is 0, 30.5. Okay, within this one, you have all the categories of age, which are young, middle, and adult, let's say. And within this, you will have all the categories of BMI. The nice thing is that you can see here, okay, this probability increase. It goes like this. Increase with what? So if you fix insulin to this one, if you look just the first bit, it increases with BMI, okay, and age, of course. So it goes, it increases, because if you have a higher BMI, you are more subject to be, you are more probably to be diabetic, right? And so it increases. But then the age is a big factor. So if you are older, then if you look at this and this one, it's going to be more likely, right, that you are diabetic, and so on. So this is a nice way. So if you instead have the insulin that is normal, this is normal insulin, your probability, yes, it is true that increase, but it is lower than the case before, because you have a problem with insulin here. And if the insulin is higher, the highest one, the highest level, then it's a problem, because these probabilities are going to be higher than the one before. So the subjects that are Worst here are the ones that have insulin that is high, okay? Then we have these subjects that are fine, let's say, because they have middle insulin, that's okay. And then we have this category is also at risk because the insulin and then the age that increases. Yes? So it's a nice way. So here we have 4 variables, okay? And we are talking about 4 variables, and we can kind of comment on that. So it's very nice. I guess it's a nice way to talk about it. Can I have just 4 minutes? And then I'll stop. Yes. Okay. Yeah, no, I'm also tired. Prediction. So when you have a data set, you want to make a prediction, you can do it in graphical model. And in this case, you want to make a prediction of the test. The function is this one, predict. So here you put new data. So these are your new data, which means a new combination or an old combination of the data that you have. And then your model, because this contains information about the conditional dependencies and the type of prediction that you want. Class means 0, 1, or you can have also probability of being 0, 1, for example. Okay, so this is what you get, and you can get at the end a confusion matrix, which I guess you're familiar to as well. Okay, so these are the values that you predicted, and then at the end of the story, you have this one. You say, okay, I have a model. How well this model predicts my outcome? And this is the answer. Okay, here from the confusion matrix, you can calculate the other stuff that I guess you know F1 store stuff like that. Yeah. Okay, so this one on the diagonal you are right. Off diagonal you make some error. So false positive and false negative. Okay, then you have true positive and true negative that are good. Okay, but check this one because sometimes the models give you good answer for let's say 0. Okay. So, but not good answer for 1. So that when the test is positive, you don't predict well. When it's negative, you do well. So it means you have a lot of stuff like here, but you have less here. So I would suggest if you are interested in one variable, then use this one. Okay. That's the conclusion. Now we have finished the theoretical part, the applied part. You have this code. Have you seen it? You have in the folder, right? What I would ask is, okay, we do a coffee break, right? We have half an hour, and then you will come back in groups. Please form groups of 4, at most 5 people, I would say. There are 3 datasets in the folder, and you can choose one of that. You can choose a DAG or an undirected graphical model, whatever you want. You run an analysis. Let's say you have 1 hour, something, and then R will pick 3 numbers, let's say, and you will present something to the others. I will suggest, okay, if you keep all the data sets, okay, all 3, I would like that one group present the first one group present the second one, and one the third one, okay? So we will do something like this. I will be here, so you can ask questions, of course. So can you make the groups, or shall I do that? Huh? I can make it. You can make it during the coffee break. Okay, don't fight, please. And yes, okay. See you.